Okay, what week of the quarter is this? Like
Six.
sixth week? So we're over the hump, we're over the middle? So, okay, that's good. That's good. Closer to graduation for some of you, hopefully. Yeah, great. So we are in the midst of understanding the electron transport chain and how it's related to oxidative phosphorylation and how standard reduction potentials can be important for, or are used to calculate the amount of energy that we can get out from the electron transport chain. So I'll go ahead and write my outline here. So the last time that we had talked, I had mentioned that the overall reaction for oxidizing NADH to NAD plus in the electron transport chain would be this reaction right here. Where you have NADH plus a proton plus 1/2 of a oxygen molecule plus will give you NAD plus H2O. And we mentioned that from the table that I gave you that the standard reduction potential for NAD plus is going to be equal to minus 0.32 volts. And I mentioned that the standard reduction potential for oxygen is going to be equal to plus 0.82 volts. And then I showed you this equation where you can relate the change in the standard reduction potential to a change in the standard free energy. So that's shown right here. And you got to be careful because these variables, well, this is a variable. You want to make sure that that makes sense. That's going to be number of electrons that are being transferred. And here, there's going to be 2 electrons transferred through this hydride that's going to be transferred. Okay, so 2 electrons will be there. And then F, as I mentioned, is the Faraday constant, which is 96.5 kilojoules per mole per volt. Okay, so that all goes in the denominator, mole times volt. And the change in the standard reduction potential is going to be the standard reduction potential of the acceptor minus the standard reduction potential of the donor. So as long as you know those, then you'll be able to calculate the change in standard free energy. And as an example, we can fill in the information for this particular reaction. So we have delta G is going to be equal to minus 2 times 96.5 times 1.14 volts. And that's going to be equal to minus 220 kilojoules per mole. Okay. So that's a very exergonic reaction. And of course, we use this to capture, we use this energy to make ATP. Now, does anybody remember the number of moles of ATP we create for every mole of NADH that's oxidized? Anybody remember that? I went over it last time. Number of moles of ATP created for every mole of NADH which is oxidized. Close to 3, close to 3. So I mentioned that books vary, but in our book it's 2.5. Okay, so there's 2.5 ATPs that are created. And so we can actually figure out the efficiency of this process. So percent efficiency in terms of converting the energy from the oxidation of NADH into the production of ATP. And the way we do this is percent efficiency is going to be equal to the delta G value for ATP production divided by the delta G value for NADH oxidation. I'm going to make that an absolute value, so it's always going to be positive, so you don't have to worry about signs. Okay, so that's an absolute value multiplied by 100. Okay. So does anybody remember what is the delta G value under standard conditions for ATP hydrolysis? So we're hydrolyzing ATP to ADP, inorganic phosphate. You have to go back to the first couple of weeks that we talked about this. Anybody remember this? What is that value for standard free energy change for ATP hydrolysis? I'll go ahead and write the reaction. ATP plus water gives you ADP plus inorganic phosphate. Anybody remember that? That's going to be what, an exergonic or an endergonic reaction? ATP hydrolysis. You guys remember? Negative? Very good, negative 30.5, which makes it an exergonic reaction, right? So delta G under standard conditions is minus 30.5 kilojoules per mole. Okay. So for the calculation of our percent efficiency, we talked about the number of ATP molecules that are created. It's going to be 2.5 multiplied by, we could say, minus 30.5 divided by minus 220. We'll take the absolute value of this. It's going to be positive anyways. And so, we got to multiply this by 100. And so if we go ahead and do that, what is that? 2.5, that's going to be about 60, 75. That's about 76 divided by 220. Maybe about 35%. Can you guys have a calculator? Probably about 30. Is it really? Okay, 35%. All right, 35%. Okay, that's just a guess, really. Okay, about 35%. So we got about 35%. The book makes a big deal about how the efficiency might be actually more, because remember, these are free energy changes under standard conditions. And as we mentioned before, that what we really care about is the free energy change under physiological conditions, which takes into consideration the amount of products and reactants we have. So they actually push this value up a little bit by using what's known as the delta G rather than the delta G under standard conditions. But if all you're given are these values, then you can just calculate this is going to be 35%. All right. Well, I told you that what drives the ATP production here, okay, so you have to think about this in reverse. What really happens, of course, is that ADP plus inorganic phosphate will go to ATP plus water. So it's really what we think is an endergonic reaction. That's going to be a positive 30.5 kilojoules per mole. How do we supply that energy? And as I mentioned last time, it's supplied by an electrochemical gradient. An electrochemical gradient. Those protons that are in the intermembrane space are, you can almost think of, if you put feelings into them, they're dying to get into the matrix, okay? And they're dying to get into the matrix because of the concentration difference and also because of the charge difference. And so we can actually calculate, if we know the charge difference and if we know the concentration difference of the inside and the outside of the matrix, we can actually calculate what that force is. And we call that force the proton motive force. Okay, so PMF stands for the proton motive force. That is the electrochemical energy stored in the proton gradient. I'll just say that. That's the electrochemical gradient stored in the proton gradient. Okay, we need two bits of information. We need to know the concentration difference and we also need to know the what's called the membrane potential. Membrane potential. And I don't know experimentally how they figured this out, but they've already figured out the pH difference across that membrane. And that pH difference, so let's think about this. The pH difference, so here's the mitochondrial, here's the matrix. This is the intermembrane space, okay? So they figured out that, let me see, I think I mentioned that you have a lot of protons here on the outside and a tiny bit of protons on the inside, okay? So they've figured out what that pH difference is, and they've also been able to measure what is the voltage difference across that. So that's the concentration difference and the pH, the membrane potential. So let's go ahead and use an equation to figure out what is, how we can relate this information to delta G, because we want to compare the delta G under standard conditions of NADH oxidation, which we already figured out was minus 220 kilojoules per mole. We want to compare that to the delta G of proton, let me just say this, of the proton motive force, okay? In other words, how much energy it takes to push out a proton from the inside to the outside. So we'll be measuring it, the amount of energy that will take to push a proton from the inside to the outside, which, by the way, is going to be a positive number. It's going to be greater than 0 because we're going against the gradient. Okay, so here's an equation that is important. So here's delta G. I'm going to write this very carefully. In to out, okay? So that's going from protons on the inside to protons on the outside. So going from the inside of the matrix to the outside of the matrix. And that's going to be equal to, oh, no. I didn't mean to do that. Okay. that's going to be equal to RT natural log of the concentration on the outside divided by the concentration on the inside plus Z, Faraday's constant, and then this thing called the membrane potential going from in to out. Okay, so I'm very careful about my orientation here. Okay, all right. What are these values? This is going to be the gas constant. The R is going to be the gas constant. The T will be the temperature. I want to make sure I get that temperature correct. So that temperature, it's got to be, okay, it's going to be temperature in Kelvin. Okay. And then we've got, this information is the amount of protons on the outside and the amount of protons on the inside. So that's the concentration. And then here we have the charge on a proton. Okay. And that charge is going to be 1. So that's easy. F, again, is the Faraday's constant. And we call this the membrane potential. Okay, so there's two components here. As I said before, this component here on the left contributes to the that contributes delta G in terms of the concentration difference of the protons, and this on the right is the electrical term, and that contributes to also to the delta G, but it's the electrical component. So this is the chemical component, and this is the electrical. Okay. Experimental. What have they been able to measure experimentally? Experimentally, they've been able to measure that the pH difference is going to be equal to 0.75. Okay. And that the membrane potential going from in to out is going to be equal to 0.2 volts. So they've been able to get that information. Let me ask you this. This pH difference, is the pH on the outside of the matrix going to be large or small compared to the inside? pH on the outside. Small, very good, very good. So actually the pH is going to be low on the outside and the pH will be high on the inside. Because you guys know that it's a negative log of the concentration of protons that equals the pH, right? Okay, so that's exactly right. So your book doesn't go through this, but I'm going to just give you a couple of hints of how to change this term right here, to pH change. You just have to know that C on the outside is going to be obviously equal to the concentration of protons on the outside, which is going to be equal to 10 to the minus pH on the outside. And analogously, concentration on the inside is going to be equal to the amount of protons, the concentration of protons on the inside, which is going to be equal to 10 to the minus pH on the inside. And I don't think we have time for this, but at the end of the day, this equation that I wrote before, we can rewrite it in terms of pH, where you have delta G going from in to out is going to be equal to RT times 2.3 change in pH, okay, plus ZF times delta psi in to out. Okay. And this change in pH is a positive number, therefore it's going to be pH in minus pH out. Yeah. Okay. So once this equation reduces to this, then it's very simple. All we have to do is plug in our numbers. So we're going to get, let's see, 0.008315 times the temperature, which is going to be 37. What is that, 310? So 310 Kelvin times 2.3 times 0.75, and then the second term is going to be plus 1 times 96.5, and then we've got this other term, which is going to be 0.2 volts. Okay, let's go ahead and just calculate this term first. I like to do this in parts. So the first term, if we put that into our calculator, if I can do that, you guys should follow along, make sure I don't make any mistakes. I'm prone to mistakes. What did you guys get for the first term? 44? 44.46. Anybody else get that? 44.46. Anybody want to check that?
Already went to the next term. I don't know.
Wait, come on. Let's go to the first term. Let's make sure we got a consensus here. 4.45. Okay. Anybody else? Let's weigh in. Yeah. 4.45. Okay, I think that's right. I get 4.45 also. Okay. But it's good to check. Okay, so this first term, just erase these other things. First term is 4.45. Okay. What about this second term? That's easier, obviously. 19.3. Okay. So what I want to show you here is that this second term dominates in terms of the contribution. So most of the energy that comes to making our ATP comes from the charge difference across the membrane, not the concentration difference. It comes mostly from the charge difference. About, what is that, about 3 to 4 times as much contribution to the charge difference. In other words, the separation of negative charges and positive charges. Okay, so let's go ahead and add these up. And if I add these up, what did we get? 23.76. Do I get a second? Okay. So, okay, write 23. Okay. 23.75, okay. We'll just take off this guy here. Okay, 23.7 kilojoules per mole of protons, basically, okay? So 73.7 kilojoules per mole of protons. So that's, and it's a positive number. It's a positive number because we're basically pushing those protons out from the inside of the matrix to the outside of the matrix. And we know the outside has more protons on it. So it takes energy. It's an endergonic reaction, right? It's endergonic. It takes energy to get out there. So it's beautiful how the math kind of contributes to our understanding of this. Yes?
What is the C in and C out?
That's the concentration. Yeah, so C in is the concentration on the inside, and C out is concentration on the outside. So we're applying this general formula. You can use this for any ion across the membrane, but we are using it specifically now across the inner membrane. And the ions that we're considering are protons, right? But C in and C out is a general term. Those are general terms. Okay, so that's how much it takes to how much energy it takes to push out a mole of protons across that membrane. Now, does anybody remember from my last lecture how many moles of protons get translocated across the membrane for every mole of NADH which is oxidized? Not 2. I think you remember there were like 3 places, right, where this happens. Complex 1, complex 6. Oh, I'm complex 6. There's no complex 6. This is still recording, darn it. Okay, complex 1, complex 3, I think complex 4. Those are the 3 places. Now, does anybody remember? You can cheat if you want to. How many protons get translocated for every molecule of NADH which is oxidized? 10. Very good. 10. Right? So if we're going to be fair in terms of calculating how much energy is going to be created from NADH, we have to multiply this value by 10. So 10 times 23.7 kilojoules per mole, okay, because we have 10 moles of protons, okay. Let me just rewrite this. I don't like that. It's not clear. Let's do this again. 10 moles of protons times 23.7 kilojoules per mole of protons. And the math is easy. That's going to be 237 kilojoules. So that value is very close to the value that we calculated for NADH oxidation, right? The NADH oxidation was supplying us with about 220 kilojoules per mole, and you could see how the math works out approximately so that this is how much energy that we get from those moles. This is the amount of energy that's found in that proton motive force that's created from that. That's beautiful. The math is matching what we see physiologically. Okay. Let's get down to what actually carries these electrons, okay, across these, what are the electron transporters? And it's actually very simple. Your book makes a big deal about this, but there's actually not much in terms of variety here. We've talked about how NADH is going to be a carrier. It's going to give it up. And it's going to give it up actually to something called FMN. And FMN is very much like NADH. It stands for flavin mononucleotide. So we've got NADH, and that's going to give it up. It's going to give up an electron to FMN. And then FMN eventually gives it up to these things called iron sulfur proteins. Iron sulfur proteins. Okay, and you know your book makes a big deal about these, but basically it's iron, okay, and it's conjugated to either inorganic sulfur, so here's a case where it's inorganic sulfur, or it's conjugated to an amino acid that has a thiol group. Does anyone remember an amino acid that has a thiol group? An SH. SH. I know methionine has S, but I'm looking for one that has an SH. Cysteine, very good. So cysteine is going to be that's going to contribute the sulfur to these guys. And basically, and I've written this before, basically this iron, which is in the 3+ state, combines with an electron, and it gets reduced to iron in 2+ state. Okay, these carriers, these sulfurs, basically just hold the iron in place. Okay, and then the electrons leave the iron, and so that's going to leave the iron, and it will toggle back to the ferric state, the iron 3+ state. So iron is one of the direct carriers of these electrons. Iron can also exist in another state within these electron carriers. And the other state are in the form of these things called cytochromes. So cytochromes are the proteins, and they have these things called protoporphyrins. And they look very much like heme. Okay? Your book has a picture of this. Let me get to the book. Where's there a picture of the heme? I'll find. Oh, here we go. Okay. So this is on page 633 of your book. And so here you have iron. It's caught in these cytochromes. And they call these structures without the iron, they call these protoporphyrins. And the iron is stuck right there. And again, the iron will be in the +3 state, and it will get reduced to the +2 state. And then it can give up electrons again. Okay, so these are the cytochromes that hold these. Okay, what about another carrier? Another carrier is copper. And copper is specifically found in complex 4. So you find copper in complex 4. And the copper can get an electron, and it gets reduced. So cupric copper gets reduced to cuprous copper. Okay? And of course, it can give up an electron as well to copper 2+. So copper is another direct binder. It binds directly to the electrons. And then there's the third item, which we haven't talked about yet, but that is, actually we did talk about it a little bit. It's called cytochrome C. So iron, copper, not cytochrome C, coenzyme Q. Coenzyme Q. And coenzyme Q is sometimes called quinone. It's another word for that. And your book actually has a diagram in terms of how that works. First of all, let's talk about this coenzyme Q a little bit. So this is a picture from your book that's quite nice because it explains it's going to bring together a couple of themes here. This is on page 640 of your book. I know they got all these fancy structures. Don't worry about that. Those are hard to interpret. But let's go ahead and orient ourselves. So the intramembrane space is down here, and this is the inside of the mitochondria up here. This is the matrix up here. So matrix up and intramembrane space down, okay? So obviously there's going to be a pumping or translocation of protons in this direction from up to down. And what we have here is complex 1. So complex 1 is going to give up electrons to Q, okay? And then I talked about complex 2. Complex 2 also gives up electrons to Q, but it comes from FADH2. Actually, complex 2 is really part of the Krebs cycle. Okay, it's succinate dehydrogenase. Okay, so that is the complex 2, and so complex 2 will take FADH2, oxidize it to FAD, and then eventually those electrons lead to Q. And then Q then will give its electrons to complex 3, and of course complex 3 gives it to complex 4, and finally oxygen is going to be reduced, and that happens in the matrix here. We're not showing you that. But I want to show you something else that's interesting about Q. Q is like this center that gets a lot of electrons, not just from NADH and FADH2 from glycolysis and the Krebs cycle. Here is another source of electrons, which we probably won't have time to talk about. But remember I talked about fatty acids and how fatty acids can be broken down through catabolism, right? And how they eventually get broken down to acetyl-CoA, okay? Well, there's ways of capturing those electrons that are in the fatty acids, and they get funneled through another pathway here. You don't have to know these names, but they get funneled through another pathway, and they eventually also will lead their electrons to Q. Okay, so you get fatty acid. Some fatty acids will give their electrons up to Q this way. And then finally, does anybody recognize where this reaction comes from? Glycerol 3-phosphate to dihydroxyacetone phosphate. Glycolysis, very good, okay? Actually, this is very close. This is glycerol 3-phosphate going to dihydroxyacetone phosphate. So it's not exactly glycolysis, but it's close to it. Anyway, there is an FAD there that can also give its electrons to Q, okay? And they're not showing you this, but glyceraldehyde 3-phosphate, which gets oxidized to NADH. NADH usually gets turned into that will go to the complex 1, but in some organs it actually feeds directly to Q. Okay, so I just want to mention that Q is very important in that it's like a center for getting electrons, not just from Krebs cycle, but from other places as well. Next thing is, what about this Q? What about the mechanism? What about the mechanism of Q? Let's see if I think I had that. Sorry, bookmarked. Come on. There we go. So let's talk about Q here. This is on page 631 of your book. So here's what we call oxidized coenzyme Q. And I want to mention a couple of things. We have this thing called the isoprene unit. And these isoprene units are always groups of 5 carbons. 5 carbons in these isoprenes. Let's count them. 1, 2, 3, 4, 5. So these are isoprene units. And you can see that they actually get conjugated one after another. And this is going to be a very hydrophobic tail. And that hydrophobic tail, there's no electronegative groups on here at all. That hydrophobic tail is important for keeping Q embedded in the inner mitochondrial membrane, okay? Now, if you go to these GNC nutrition stores or something like that, you might find something that says Q10 or Q20 or Q30 or even Q50. You'll see that on the label there, okay? What do those mean? That is actually the number of isoprene units on Q. So if you get Q50, basically you're getting something that has 50 of these isoprene units attached to it. That's a big hunkin' molecule there, okay? That you'll, I mean, if you want to, you'll ingest, okay? There's a question about whether these antioxidants really are helpful. I have my own opinions about that, but anyway, we won't go there. But I want to show you about the mechanism. And the mechanism here is basically one electron movement. So similar to what I showed you with FAD, you have to look at arrows with only a half of a head on them. Okay, these are one electron movements. And so here we have a proton plus an electron. Actually, I'm going to just combine those to make a hydrogen atom. Okay, that hydrogen atom is going to attack right here at the end of this oxidized coenzyme Q, and then you get this this sort of radical reaction here until finally you end up with an unpaired electron on the oxygen that's on the opposite side of this coenzyme Q. Okay, and we call this intermediate form. We call that the semiquinone. Semiquinone. And we call this one actually quinone. Oh, I like that. This word, O-N-E, do you guys remember your organic chemistry, what that means? What does O-N-E mean at the end of a term there? What kind of a functional group does an O-N-E stand for? A ketone. Wonderful, ketone. And so what you see up here are two ketones. That is a ketone there, and there's a ketone here, okay? So this is called quinone, actually, okay? It's also known as oxidized coenzyme Q. And this is called the semiquinone, like it's a half a quinone, okay? So basically, one half of it is, it's close to a ketone, but not exactly, okay? And then finally, we're going to get reduced coenzyme Q, which has two alcohol groups on them. Okay. Okay. So and that happens by just having this extra hydrogen, another hydrogen come on, and it's going to just bind with that unpaired electron that's on the oxygen, and so now we have reduced coenzyme Q, which basically has two alcohol groups. No more ketones on here. Okay, so that's the mechanism for this quinone. Next, I think we're ready to talk about ATP synthase, and then we'll talk about inhibitors. So just to jog your memory, recall, so we'll talk about ATP synthase. Okay. Sorry. And so recall that we've got complex 1, we've got complex 3, we got complex 4, and then we've got ATP synthase. I know we have complex 2 as well, so here's complex 2. Wait a second, I'm missing something. Oh yeah, coenzyme Q, that sits right there. Cytochrome C, that sits right there. And this is the matrix on the inside here. And this is the intermembrane space out there. And so electrons are flowing in this direction. Okay, what happened to my, so there's 4. Okay. And then what happens is that oxygen is going to get reduced to H2O. And we have all these protons out here. And these protons go through the ATP synthase. And as that happens, ADP is going to get converted to ATP by combining with inorganic phosphate. So we're now talking about this ATP synthase part. And ATP synthase is composed of two parts, something known as F1 and F0. And I think these are named because that's the way they were purified. I think these probably fraction 0 and fraction 1. That's probably how they were purified. I'm not sure. This is a membrane protein. Okay. Whereas F1 is only lightly attached to the membrane. Okay. And they found, obviously both of these are necessary in order to produce ATP. And what they found, this is actually Boyer's group at UCLA, who got the Nobel Prize in the late 90s. And I actually worked across from his laboratory when he was making a lot of these discoveries. I didn't realize he was such a big deal at that time. So I guess I should think about that more and reflect that I should probably offer him some respect. But he used to mess up our cold room. We had a cold room that they would take over for 3 days because they would do these big preparations of ATP synthase from spinach. And so they would buy tons and tons of spinach. And after them doing their preparation, I would go in the cold room, and the walls were just all green because of their prep. Okay. And what he found is that basically this ATP synthase acts like a oh no, don't stop. I don't believe that. Hopefully you guys took good notes.
We can pause the video right before that happened though, right?
Yes, you could. You could pause it. Yes. Okay, here it is. All right, we got it back. Whew. Okay. So what they found was that there's a rotary mechanism for ATP production. And the next time we meet, I will hopefully have a video that will show you this rotary mechanism. Beautiful video showing a single molecule, showing that there's this arm that rotates in the ATP synthase. You guys have a wonderful day, and I will see you on Friday. Oh, I'm going to put up a new sapling learning for chapter 15. So I'll have that ready for you. And I think there might be a sapling learning due today. So is that right? Did I make it Friday? Okay, Friday. Is there one due today? Okay, there's a one due today and there's one due on Friday. So make sure you guys get it done today. I think before 10 o'clock or something, or 8 o'clock. 8 o'clock, okay. All right, have a good day.